So at this point, we know what left-leaning red-black trees are, we know that they're efficient, and now we just need to know how to build them. So as I mentioned many times, there exists some one-to-one mapping between a 2-3 tree and an LLRB. So the implementation of our LLRB insert operation is going to be based on maintaining this one-to-one correspondence. So whenever we're performing an LLRB operation, we're going to pretend like we're a 2-3 tree. And preserving that correspondence is going to involve tree rotations. We're going to use rotations so that we can behave like a 2-3 tree. So we're going to do this in 4 parts together. Let's now invent the idea of red-black tree insertion. So first question. Let's suppose we have a red-black tree which has only one node, S. At the bottom, I'm showing the corresponding universe if we're thinking about 2-3 trees. So this is LLRB world, and this is the 2-3 tree world. So if we add E to this tree, we have 2 choices. We could either add it as the left child of S with a red link or a black link. And so I want you, this is a kind of easier warm-up exercise, so tell me which one of these 2 gives you the correct representation of the corresponding 2-3 tree. So hopefully this one should be trivial, and it's going to be this top answer. In 2-3 trees, we are always going to add items using a red link. So just like in 2-3 trees, where new values are always added to a leaf node, it'll be added inside the leaf node, we're going to use a red link to represent that fact. Okay? So let's try something a little more challenging. So usually in a 2-3 tree, if I have here A, B, and E, where everything is a 2 node, and then we add S, well, what happens is we end up with S inside the same leaf node as E. So here, if we do what we just said in the previous slide, where we use a red link when we add to the corresponding LLRB, the question is, what do we need to do to fix this? So if we insert S, add a red link, as we've claimed we should do, what should we do in order to ensure that our mapping to our 2-3 tree is correct? And the problem here, first, I guess you should figure out what the problem is, and then second, try and figure out what we should do about it. Okay. So the problem is that this link should not be leaning right, and so to fix it, we can use rotation. In particular, we can rotate E to the left. So E and S, you think of them as temporarily merging, and then E goes off to the left. And now we have the correct representation. So we're halfway there. Okay. So I'm going to introduce a definition, or a rule, which is that in 2-3 trees, we have these temporary 4 nodes. So for example, if we have A, B, E, S, if we add Z, we're going to temporarily represent a 4 node by adding a Z to this 3 node. Okay. So the thing I'm just giving away for free in terms of how red-black trees should behave, I'm going to say we're going to represent temporary 4 nodes as a BST node with 2 red links. Now you may say, this seems like a direct contradiction. Earlier, Josh, you said that no node should ever have 2 red links, and that's true, but this is just a temporary violation. Just like in a 2-3 tree, no node can have can be a 4 node, but we allow temporary 4 nodes. So here we'll allow temporary left-right links. Okay. So why am I telling you this? Well, because that's your next puzzle. So let's suppose we have the LLRB shown here. It's valid. This is the corresponding 2-3 tree in the 2-3 tree world. When you add E, you get a temporary 4 node. But if you just do everything the way we've been describing so far, then when you add E, it ends up being linked below this S, and so we have the wrong 4 node representation. So what I'd like you to do now is figure out, how do I change my tree so that the tree has, so that the temporary 4 node is represented as a node with 2 red children. That is 1 left red child and 1 right child. Because I said earlier that this is the way we need to represent things. So tell me, what do I need to do to this tree in order to make it correct? So it's going to be a single rotation. So tell me which rotation and which direction, or left or right, and which node to rotate. Okay, so in this case, what we need to do is rotate Z to the right. So Z and S will be temporarily merged together, and then Z gets shot out down and to the right. Okay? And so we end up here with the correct representation of our 4 node. And then lastly, this is the hardest puzzle I'd like you to try and solve, which is in a 2-3 tree, when we have a 4 node, we have to split this node and send B up and make A and C into their own nodes. So now, and this is the hardest challenge of all, but I really want you to spend, maybe 5 or 10 minutes, if you aren't getting it, to try and get this at least. It's an interesting puzzle, which is what would be the corresponding operation we need to do with left-leaning red-black trees so that we get this, so that we're properly representing this 2-3 tree. And the way to start is, if you don't know where to start on this problem, is let's draw the equivalent LLRB for the final state that our 2-3 tree is going to end up in. Okay? So draw what's going to be here, and then figure out what would be the equivalent operation. Okay, we give you a hint. So the hint is that it does not involve any rotation. Okay. So the thing to do in this case is a color flip. So I'm going to use an operation called flip B that flips the colors of all edges that are touching B. So its children become black links, and its parent link becomes red. Now I should note, this doesn't change anything about the structure or shape of our binary search tree. It is no more balanced than it was before. Now the reason we're doing this is because we're trying to maintain this perfect one-to-one mapping. That's it. So here it doesn't actually change anything about the shape, but we're doing this so that the mapping is correct. And so here in this case, it's nice because the binary search tree was effectively already balanced as much as it could be, and we're just doing this for bookkeeping so that future rotations will work. Now bizarrely, we're done. Doesn't feel like we've done anything, okay? It seems like all we did was a few really trivial cases, so how could this possibly work, okay? Well, what you've just done is invented the rules for a red-black binary search tree, so they're not so bad. This is the full set of rules. So when you're inserting, use a red link. If there's a right-leaning 3 node, well then we have a left-leaning violation. So we need to rotate left the appropriate node in order to fix. So if we ever have a right-leaning node, we swing it to the left. If there's 2 consecutive left links, our problem is that we have an incorrect 4-node violation, right? We're not allowed to have 4 nodes that are represented as 2 consecutive left links, so we're going to rotate right so we have the proper representation of a 4 node. And then lastly, if you ever have nodes with 2 red children, that means we have a temporary 4 node that needs to be split. So in order to emulate the split operation in a 2-3 tree, we're going to color flip the node. That is, all edges touching the node will flip. Okay? And that's it. So it turns out just these 3 relatively simple ideas will work. So there's one last detail I want to drive home, which is that occasionally we have cascading operations, where one of your fixes, that is your rotations or your color flips, that it will cause an additional violation that needs fixing. So for example, let's suppose we have an LLRB as shown. We add Z, which creates a temporary 4 node. We then color flip, which gives us a red-leaning right red link, which is not great. So we need to fix this somehow. Okay. The corresponding 2-3 tree, by the way, is that we added Z, and then we split that node, sending S out. So right now, we're close, right? But this is not the correct representation of our 2-3 tree. This LLRB is wrong because that's a right red link. So what do we need to do next? Let's try and figure out what needs to happen next. So whenever we have a bad right link, when we have a right-leaning red link, that's here. We have a left-leaning violation. We should be left-leaning, but we're right. So we're going to rotate left the appropriate node to fix. So who do we rotate to the left? Well, it turns out it's B. So I rotate B to the left. We think of B and S as temporarily merging, and then B gets shot down and to the left. So maybe just to summarize what's going on here, there's 2 different ways that you can imagine representing this 2-3 tree. But our rules is that it needs to be left-leaning. We must here have a left-leaning red link. Okay? So this rotation operation, make sure we have the proper mapping. Okay? So maybe I'll take a break here, and then in the next video we'll talk a little bit about runtime. But that's actually it. That's all the operations that you need in order to do BST LLRB insertion.